Rates of reactions. Here's a definition of rate. Rate is a description of a change in a quantity over a given time interval. You can calculate the rate by taking the change in the quantity and dividing it by the change in time. How then do you find the reaction rate? Well, by definition, the reaction rate is the change in concentration of a reactant or product per unit time. So the reaction rate is concentration change in final, subtract the concentration rate in initial, divided by the final time minus the initial time. So this would be the change in A divided by the change in T. Average rate of change, then, is the measure of the average change in the concentration of a reactant or a product per unit time over a given time interval. If you were to draw a concentration time graph, the average rate of reaction is represented by the slope of the line that is drawn between the 2 points on the curve. This line is called a secant. The instantaneous rate of change is the rate of the reaction at a particular time. To find the instantaneous rate of a reaction using a concentration time graph, draw a tangent line to the curve and find the slope of the tangent. A tangent line is like a secant line, but it touches the curve only at one point. It does not intersect the curve at 2 points. So here is a graph comparing the average rate of change for a secant, shown in green, and a tangent, shown in red. Reaction rates in terms of products and reactants. Given this equation, for the rate of the following reaction in terms of the production of oxygen, 2N2O5 produces 4NO2 plus O2. There are two other ways to represent this rate of reaction. In terms of the rate of disappearance of dinitrogen pentoxide, or in terms of the production of nitrogen dioxide. For every 1 mole of oxygen that is produced, 4 mole of nitrogen dioxide are also produced. This means that the rate of production of nitrogen dioxide is 4 times greater than the rate of production of oxygen. Therefore, the rate of production of oxygen is 1/4 the rate of production of nitrogen dioxide. You can express this relationship between oxygen production and nitrogen dioxide production as follows. For a concentration of O2 divided by the change in time is equal to 1/4 times the change in concentration of nitrogen dioxide divided by the change in time. When 1 mole of oxygen is produced, 2 mole of dinitrogen pentoxide are consumed. Therefore, the rate of production of oxygen is half the rate of disappearance of dinitrogen pentoxide. So you can represent this relationship as the change in concentration of O2 divided by the change in time is 1/2 the concentration change in dinitrogen pentoxide divided by change in time. The expression involving N2O5, the reactant, has a negative sign. The change in concentration is calculated using the expression below. Change in concentration is the final concentration minus the initial concentration. Since the concentration of a reactant always decreases as a reaction progresses, the change in concentration is always negative. By convention, however, a rate is always expressed as a positive number. Therefore, expressions that involve reactants must be multiplied by -1 to become positive. Now we're going to look at this problem again. Dinitrogen pentoxide, N2O5, decomposes to form nitrogen dioxide and oxygen. If we write this as an equation, 2N2O5G produces 4NO2G plus O2G. NO2 is produced at a rate of 5.0 times 10 to the negative 6 mole divided by liters times second. What is the corresponding rate of disappearance of N2O5 and the rate of formation of O2? Let's look at what is required. Since N2O5, dinitrogen pentoxide, is the reactant, you need to calculate its rate of disappearance. O2 is a product, so you need to find its rate of formation. So what is given? Well, you know the rate of formation of NO2 and the balanced chemical equation. So let's plan our strategy for solving this. First, check that the chemical equation is balanced. Then use the molar coefficients in the balanced equation to determine the relative rates of disappearance and formation. Since 4 mole of NO2 are produced for every 2 mole of N2O5 that decompose, the rate of disappearance of N2O5 is 2 to 4 or 1 to 2, the rate of formation of NO2. Similarly, 1 mole of O2 is formed for every 4 mole of NO2. Therefore, the rate of production of O2 is 1/4 the rate of NO2 production. So now we can act on our strategy. So we can calculate the rate of disappearance of N2O5 is equal to 1/2 times 5.0 times 10 to the negative 6 mole per liters times second, given in the question, equals 2.5 times 10 to the negative 6 mole divided by liter times second. So the rate of production of O2 is 1/4 times 5.0 times 10 to the negative 6 mole divided by liter per second, which is 1.2 times 10 to the 6 mole divided by liter times seconds. So check our solution. From the coefficients in the balanced equation, you can see that the rate of decomposition of N2O5, dinitrogen pentoxide, is 2 to 4 or 1/2 the rate of formation of NO2. The rate of production of O2 is 1/2 the rate of decomposition of N2O5. So let's take a look then at some factors that affect reaction rate. Number one, the rate of reaction can be increased by increasing the temperature. Increasing the concentration of the reactant usually increases the rate of the reaction. A catalyst is a substance that increases the rate of a reaction. The catalyst is regenerated at the end of the reaction and can be used again. More on this coming up. Increasing the available surface area of a reactant increases the rate of a reaction. The rate of a chemical reaction depends on what the reactants are. Consider the general reaction below. This reaction occurs at a constant temperature. The reactant formulas are represented by A and B. The stoichiometric coefficients are represented by A and B. In this section, you will study reaction rates that are not affected by the concentration of the products. Therefore, you do not need to use symbols for these products. In general, the rate of a reaction increases with the concentration of the reactants when the concentration of the reactants increase. The dependence on the rate of reaction on the concentration of the reactants is given by the following relationship. The rate is proportional to the concentration of A times a value M times the concentration of B times a value of N. This representation or this relationship can be expressed in a general equation called the rate law equation. For any reaction, the rate law equation expresses the relationship between the concentrations of the reactants and the rate of the reaction. The letter K represents a proportionality constant called the constant rate, or the rate constant. This is a different rate constant, there is a different rate constant for each reaction at any given temperature. The exponents M and N must be determined by experiment. They do not necessarily correspond to the stoichiometric coefficients of their reactants. They are usually 1 or 2, but values of 0, 3, and even fractions can occur. So we have rate equals the rate constant times the concentration of A to the exponent M times the concentration of B to the exponent N. The values of the exponents in the rate law equation establish the order of the reaction. If a given reactant is found to have an exponent of 1, the reactant is said to be first order in this reactant. If the exponent of the reactant is 2, the reaction is second order in this reaction. The sum of the exponents M plus N is known as the overall reaction order. So if we have the sample rate equals K times the concentration of A to the exponent 1 times the concentration of B to the exponent 2, this rate law equation below represents an equation that is first order in concentration A, second order in concentration B, third order 1 plus 2 overall. So let's take a closer look now at the rate constant. The magnitude of the rate constant, K, indicates the speed of the reaction. A small rate constant indicates a slow reaction. A large rate constant indicates a fast reaction. Let's take a look at an example. A first order reaction with a rate constant of 10 to the exponent 2, s to the exponent negative 1, will essentially complete in less than 10 seconds. But a first order reaction with a rate constant of 10 to the exponent negative 3, s to the negative 1, will take approximately 2 hours. As the reaction proceeds, the reaction rate decreases because the concentrations of the reactants decrease. The value of the rate constant, however, will remain the same throughout the reaction. In other words, for a given reaction under constant conditions, the value of K remains constant. Since the rate of a chemical reaction depends on temperature, so does K. The value of K must be accompanied by the temperature at which the reaction occurs. And here is an example. For a second order decomposition of hydrogen iodide at 440 degrees Celsius, K is equal to 2.7 times 10 to the negative 3 liters divided by mole times second. When the temperature is increased to 500 degrees Celsius, K is 3.9 times 10 to the negative 3 liters divided by mole times second, mole second. Defining first order reactions. The first order reaction has an overall order of 1. The decomposition of dinitrogen pentoxide N2O5 is an example of a first order reaction. Through experiments, we can see that this reaction is first order. So we would write the law equation, the rate law equation, as the rate equals K times the concentration of N2O5 order 1. Because the overall order of the reaction is 1, it is first order. Reactions with more than one reactant can also be first order reactions. For example, consider the following reaction. CH3 plus H2O produces CH3OH plus H positive plus Br negative. Experiments have shown that the reaction is first order in CH3,3CBr and 0 in water. In other words, the rate of the reaction does not depend at all on the concentration of water. So the rate law equation would be K times the concentration of CH3,3CBr to the exponent 1 for first order, and the concentration of H2O to the exponent 0 as it is 0 order. So the overall reaction order is 1 plus 0, which is 1. So this makes it a first order reaction. So now a second order reaction. Here is an example. 2HI produces H2 plus I2, hydrogen iodide. Chemists have determined by experiment that this reaction is second order in hydrogen iodide. Therefore, the rate law equation is written as the rate is K times the concentration of HI to the exponent 2 for second order. An example of a second order reaction is the reaction between nitric oxide and ozone, shown in this equation. By experiment, chemists have determined that the reaction is first order in nitric oxide and first order in ozone, as shown by the rate equation. Rate equals K times the concentration of NO to the exponent 1 times the concentration of O3 to the exponent 1. This means then that the overall order of the reaction is 2, 1 plus 1. Therefore, the reaction is a second order reaction. So in the next video, we're going to learn how to use rate experiments to calculate the rate constant and the rate order. Stay tuned.